All right, I think I'm ready. Good morning, everybody. So we are going to continue talking about volumes by cylindrical shells. By the way, our first homework assignment is due tonight. I hope you've had a chance to check it out. Do it by midnight. Let me know if you have any questions. I hope it works out for you. All right, volumes by cylindrical shells. So the idea is if you have something like this shape, which is made by taking this area and spinning it around the y-axis this way, you get some kind of a weird kind of bowl type volume. And the cylindrical shells concept is you slice it into these sort of, well, they call them cylindrical shells that have this kind of shape to them. They're like solid. Ugh. Look at that picture, huh? That's what you get at 9:02 in the morning. They are sort of solid, pipe shapes or cylindrical shells, as they call them in the book. These things, they have a volume that's not so hard to figure out individually, and realizing what the volume of each of those shells is, the volume of the entire shape is the integral from a to b of, well, this is the formula, 2 pi x f of x dx, where f of x means the height of the shells, where in this example, in a simple example, the height will just equal whatever this function is, all right? Although in some cases it can be a little more complicated than that, but typically the height will just be the function. That's why I wrote it as f of x. And then the a and the b, it's important to notice, because of the strategy that is used in drawing the shells, the a and the b are here and here. You may be tempted to put a all the way on the left side of this picture, but it's not. Because of the way these shells are constructed, the very smallest shell is like in the middle, very sort of skinny, and then as you go out this way, the shells get wider and wider. But you don't start the a value back here. You start the a value in the middle, and the shells sort of grow from the inside out. That's why the lower integration value has to start sort of in the middle, not on the leftmost side. All right, this is the formula, so I just want to do some examples using this formula. Are there any questions about that so far?
The way that shape would appear if you were like looking down on it from above, I'm a little confused. Would it kind of look like a pool, like a circular pool?
The black shape, you mean?
Yeah, yeah. Once
Yeah.
you rotate it around, like kind of towards like the z-axis, I guess, it kind of appears like a pool, right? Like a open bowl.
Yeah, right, exactly. The sort of the inside is kind of bowl-like, but the outer edge is just like a flat cylinder, right? Yeah. That's what the shape would look like. It's a little tricky to visualize. All right, let's try some examples. So this example that I just drew right there, this would be, let's say this function was f of x equal x squared, and I went on the picture from 0 to 1 here. So in this example, for f of x equal x squared, and specifically, I'm just going to draw it again, going over to 1 like this, right? We get the volume is going to be, just using the formula there, integral a to b. Now, like I said, in this case, the b is 1, the a is 0, because the a to b sort of starts from the inside out, not from all the way to one side to all the way to the other side. And then, anyway, it's going to be 2 pi x, and then x squared dx, because my function this time is x squared. So this, of course, is 2 pi x cubed dx from 0 to 1, and then I can just do the integral of that. It's going to be 2 pi 1/4 x to the 4. Plugging in 0 and 1, I plug the 1, I get 2 pi 2 pi times 1/4 times 1 to the 4 minus a whole bunch of stuff times 0, right? So the whole thing is just 2 pi times 1/4, which is, of course, pi over 2. All right. As usual, the integral here was easy. The setup is the more interesting part. Are there any questions about that? That's a particularly easy example. I would like to point out, you could also do this if you wanted to. You could do this using the washers, which is what we spent most of the time talking about, slicing sort of horizontal slices with the washers. All right, if you wanted to, you could have done this. So you could have done washers in this case. Washers, all right? It's a little trickier because if you want to do the washers in this example, you have to do it in terms of the y-axis, which means you have to rearrange your function as a function of y instead of x, which is not a big deal. Instead of the square y equals x squared, you'd use x equals square root of y, but it would still work. And also this becomes like one of those things with the outer radius and the inner radius, which you would have to think through a little bit. But you should, you know, if you work that out really, you should still get the same answer of pi over 2. In general, if I ask you to do one of these on a test or something, I might not say which method to use, in which case it would be up to you to decide which one would be easier and which one you want to use. Or maybe I'll tell you, you got to do it using the shells or whatever, if I just want to make you do it a certain way. All right. All right, I want to try a few more of these. Now, sometimes these end up giving you integrals which are hard to do. But like I said, I want to focus more on the setup because the integration part is more or less routine. So let's do a few examples where we just set them up. Now, some of these you could actually do the integral. Some of them would require some fancy tricks which we haven't talked about yet. But anyway, I just want to talk about setting them up because that's the more interesting part. So let's try find the volume. I mean, that's what all these questions are going to be about. Of how about a similar picture, only it's going to be one sort of loop or one bump of the function sine of x. And then you spin this thing around the x-axis, all right? So it looks like this, kind of. Now that picture as drawn looks like a certain anatomical feature, but actually the volume that you get actually doesn't look like the anatomical feature that I have in mind because it's spun around this way, so it's rounded sort of in this way, right? All the way around. It looks kind of like a bundt cake pan, you know, like the coffee cake shape, you know, in a ring, right? Only there's not like a. It actually comes together in a point in the middle. All right. Okay. Anyway, let's try to find that volume where this function is sine of x. All right. So you know we're going to use the same old formula. I'll just write the formula again. A to b 2 pi x f of x dx, where f of x is the height of the shells. Let's talk about the a and the b first of all. The a and the b, remember, should be this point and this point because that's how you got to set up the cylindrical shell thing. So it looks to me like the a is 0, right? Anybody want to say what's the b going to be? You just have to think about if I'm using the function sine of x, where actually is that point, the x value?
That one going to exist at pi?
Yeah, pi. This is where sine of x comes back down to 0. So the b here, you know, the a in this case is 0. The b is going to be pi, and that's just because you have some basic knowledge of sine of x. All right. So I'm going 0 to pi. Okay, and then my function on the inside, 2 pi x is always part of the formula, and then f of x is the function which gives you the height of the shells. And that function is sine of x. No tricks going on here. So the function is sine of x. All right? And this is the setup. All right? I just want it, like I said, I just wanted to do the setup. Now this integral is hard to do. You can't do this integral using the u substitution. You can do it with a trick called integration by parts, which you are going to do later on in the semester, but I think I'm just going to leave it at this. We set it up. This is a little bit of a tricky integral to do based on the tricks we have so far. All right. Any thoughts about that?
So, if we have a quiz, do we have a quiz on Friday?
Yes, we do.
If you're looking for an answer on a quiz on Friday, are we going to be setting these up, or would you expect us to solve this all the way out?
I would tell you per question. So yeah, I mean, if I intended for you to stop at this point, I would definitely tell you to stop at this point. If I don't say anything, I would expect you to do the whole thing. Although, you know, during a test or whatever, you can always ask me, is this enough? And I'll tell you. All right, great. Let's try another one. How about we did some examples of this form last time. Let's try something that looks sort of like a Christmas tree stand kind of thing. Remember this thing? We did some of those last time. Now, last time we did these using the washers method. Let's try it with the cylindrical shells method this time. All right. So this is let me just be a little specific about what exactly I'm talking about here. That picture is not terribly helpful in seeing the details here. So I want this to be 1 here and 2 here, and then this is a you know, a line, right? And up here is 1. I think that's enough information to determine everything about everything you need to know about this picture. All right, and then it rotates around this way. Let's find that volume. All right, of course, we got the formula. 2 pi x f of x dx. All right, we got to plug in various things. What do you think, first of all, about the a and the b?
Would it be -1 and 1?
I don't think so. We want, remember, when you're doing the cylindrical shells here, the a and the b are only on one side, going from the beginning of the sort of the x value, the beginning of the shape.
1 and 2.
Yeah, it's going to be 1 and 2 in this case. The a and the b are 1 and 2. So a is 1, b is 2. Right? You look at the picture, the part of it which is sort of contributing to the volume, and you just go across that part of it once for the a and the b. All right, what about f of x? I guess that's the only other ingredient here. Now this one is a little bit tricky. You have to figure out what is the equation for that line, right? The f of x, of course, is the function which determines the height, and really what we need is this equation of this line here. Any thoughts about that? You could think of this maybe, I mean, I don't know if anybody has memorized like the point slope form of a line. I always have to think it through a little bit when I try and do that. The slope and intercept form is the easiest one for me to think through. If I have 1 and 2 here, and this line goes like that, where that's 1, and can anyone sort of guess the slope and the intercept here? Yeah, Dan?
Would be y equals -x as the equation for a line.
That's pretty good. -x, so that's the downward slope. I think if you have the slope and intercept form, there is an intercept here, right? You want the mx plus b, what's it going to be?
Oh yeah, it would be +2.
+2, yeah, great. Excellent. So this is the what I'm going to use for f of x, right? This is f of x. All right, so in this case, you got to do a little bit of figuring to decide what exactly the equation for the f of x is, but it's a line, so not a big deal. All right, great. Let's just do it then. So it's going to be volume is okay. So it's going to be integral 1 to 2, because that's the a and the b, and then I got 2 pi x, and then I got f of x, which is minus x minus 2 dx. And now we got to do this integral. This is not a hard integral. I have just sort of polynomial type stuff on the inside. We can distribute first on the inside. Remember, you gotta you should try and simplify as much as you can the integral before actually doing the integral. So, and I'm going to take the 2 pi out like I usually do. distribute on the inside. I got minus x squared minus 2x, right? Now we can do the antiderivative. 2 pi times, what do you say? Someone want to shout out, what's the antiderivative?
Professor, why would it be minus 2 in the parentheses?
Oh, I messed it up. Yeah, thank you. This is plus 2 here. I changed it to a minus 2. I don't know why. It should be plus 2. Plus 2, right? How you like me now? Yeah, okay, great. Okay, so what's the antiderivative?
Negative 1 over 3x to the third plus x squared.
Yeah, excellent. Great. And then I put my 1 and 2, right? And you plug the numbers in. We get 2 pi times minus a third times 2 cubed plus 2 squared minus 2 pi minus a third times 1 cubed plus 1 squared. There you go. That's the answer, the volume. All right. Any thoughts about that one? This is the volume using cylindrical shells. It's great. All right, I got one more that I want to try and set up, and then I had one for you guys to try. How about Oh yeah. Okay, so this is another one where we're just going to set it up because the integral we end up with is a little tricky. I will remind you that actually this example, I meant to mention this before. This example here, you could have done using the washers by slicing it across this way, right? And you get ordinary looking washers, which, I mean, you remember, we did some examples just like this last time using the washers. This one, though, is much harder to do using the washers. And it's not immediately obvious why it would be harder, but if you think about it, this shape, looking like this, right? If I wanted to, instead of the shells, do the washers, the strategy would be to slice it up this way, right? The problem here is the outer radius and the inner radius would be difficult to determine that as a function, right? The standard trick is to write the function sort of the other way around, right? This, written as this way, is y equals sine of x. How do I translate that into a function of x? X equals what? You have to solve y equals sine of x. Solve that for x. This is not obvious how to do that. There is something called the inverse sine function or the arc sine. I don't know if you ever heard of that. But even that is difficult to use in this context because I have two different points. And like, what's the inner radius and the outer radius? These are both points of the same function. Because they both come from sine of x. So it's not obvious at all how you would do this part, all right? Now, so this is an example where doing the shells is actually easier than doing the washers, because doing the washers is it's very hard to rewrite this function in terms of y. I meant to mention that before. That's why the shell method exists at all. You know, I'm not just... They didn't just come up with this idea just for fun. There are certain examples which are a lot easier to do using the shells, and certain are easier to do using the washers. All right, anyway, here's another one which is quite difficult to do using the shells, but at least you can set up the integral without too much trouble. Sorry, I meant to say it's difficult to do using the washers, but using the shells it's easier, at least to set it up. I would like to find the volume of a torus. Torus is the mathematical word for the a donut shape. Now, how do you make a donut shape? You would take a circle over here and spin it around the x-axis. So, in particular, I want the torus. I'm going to redraw that. I want the torus that looks like this. So it has sort of a unit circle over there, and then you spin this around the y-axis. And you get, you know, it ends up giving you another circle over here, and then it's this kind of a donut-y shape. All right, how's that look? That's the donut-y shape. I hope you can imagine what I am trying to draw in that picture. You want to here's a little pro artistic tip. You can amaze your friends at your skills in drawing a donut shape. This is not it. What I just drew doesn't look great. Here's the trick. You ready for this? It's a simple 3-step process. First, draw like a big oval. All right. Then put a little smiley. Doesn't look so much like a donut yet, but check this out. How you like that? It's delightfully simple to draw, and it looks great. Okay, so that's the shape I'm talking about, a torus. All right. I would like to find the volume. Again, this is a situation where the washer method does not work very well, because if I try to slice it up this way, then my outer radius and my inner radius end up being 2 points of the same function, and it's very hard to write that function in an appropriate way so that you can set up the washer calculation. But the shells is quite a bit easier, so don't try to do the washer method. That is not going to work in this example. But if we do the shells, then all we have to do is look at, in fact, there's a little trick that makes it even easier. Let's just do the top half and then multiply the answer by 2. So instead of actually considering this whole circle, I'm only going to consider the top half. This makes it even easier. The shell method will just use shells with heights like this, which are given by the function height, and that's all there is to it. All right. So this is going to work out pretty nicely. Of course, the other half is over here, but that doesn't matter so much. All right. So for our f of x is going to be just this function here, right? This sort of, I'm not trying to point at the point there. This half circle type function. And we did an example kind of similar to this. Was it last time? I don't know. About something involving a half circle type function. The way to get the half circle function is to start with the basic equation for a unit circle is like this. This is a unit circle at the origin. Now, in this example, the circle is not based at the origin. I don't know if you remember how to do this, but the center of this circle is at x equals 2. So we're going to use the way that this formula works out is this. This is the unit circle with the center at 2, 0. All right. This is something I'm sure you learned how to do at some point in your youth, the equation of a circle. If you wanted a circle with radius r, you'd, instead of 1 over there, you'd have r squared. But this, in our case, is supposed to be a unit circle. Okay. And so how do we get the formula for the heights there? I need to solve this for y. So as a function, I need to solve for y. Anybody want to try that? How do you solve this for y?
Just subtract x minus 2 squared.
Okay.
Do the square root on the other side.
Yeah, great. Subtract like that and then take the square root. Now, of course, when you take that square root, you're only going to get the top half of the graph, but that's fine because that's actually all we wanted was the top half of the graph. All right. So this is my function. And if you want, you could square out that thing and inside the squared sign and recombine it with the 1. It's not really helpful to do that, but you can if you want. All right. I think we're ready to write the volume, right? So my formula is integral a to b 2 pi x f of x dx. What are the a and the b going to be?
Going to be 1 and 3.
1 and 3, yeah, I like that. This is my region here. the A and the B, when you're doing the shells method, start sort of on the, of course the whole thing is over here too. You start on the kind of inner part and you work your way outwards to the outside, which is 1 to 3. Great. So I am going to say, in our case, I'm going to put a 2 out front. Remember I said this is because we only did the top half, and I said we were going to multiply the whole answer by 2. So this is because we did the top half, and then we multiply by 2. I said we were going to multiply the whole answer by 2, so that's where that 2 comes from. It's not typically not part of the ordinary volume formula, just because in this example we're doing a special trick where we're multiplying the whole answer by 2. Anyway, 1 to 3, 2 pi x f of x dx. All right, and this is my answer. What are your thoughts about that? Any questions about that one? This is a difficult integral to do now. You might think of doing a u substitution. You choose the u to be the inside of the square root sign, but it turns out then the du would be messed up. You wouldn't get something with just x in it for the du. So I'm just going to leave this as a somewhat hard integral to do. You could plug this into a computer, of course. I hope you know there are computer integral machines you can, websites you can use to find integrals of things. Type it in. It'll tell you if you really want to know. All right. Any questions about that? The torus. Excellent. I got one for you all to try out. See what you think. I'll give you a few moments here. Let's find the, let's use the shells to find this volume. This one you should be able to compute all the way. So this is the shape rotating around this way. All right, and the function here is y equals cube root of x. That's the function I want to use. And it goes up to 1 here. All right, see what you think. I'll give you a few moments. Try it out. I give you 1 more minute. All right, it's been one more minute. I hope that you feel like this one is pretty straightforward one. You just sort of plug everything in and it works out. There's no real tricks that you have to do. I'm going to use, what did you use for the A and the B?
I went 0 to 1.
0 to 1, yeah. 0 in the middle, and then it goes to 1 at the outside. Great. And then I got 2 pi x. And then what's my function f of x?
Third root of x.
It is cube root of x, yeah. Not a lot to say about that. You don't have to figure anything out because I just straight up told you the function. And then we might as well do the integral. What's your strategy for doing the integral? The 2 pi can come out, as always. How do you handle x times cube root of x?
You change the cube root of x to x to the 1/3.
Yeah, right.
By x.
Yeah, so it's really x times x to the 1/3, and what does that simplify to?
I got 3 over 7x to the 7/3, but I have a feeling that's incorrect.
Maybe. So before the integral, what do you have?
2 pi. Sorry.
Yeah, x to the 4/3 is what I'm looking for. Yeah, I think what you said is correct. Now we're going to do the antiderivative. You got to increase the power by 1. It's now 4/3. If you add 1 to that, you add 3 more thirds, which makes it 7/3. So 2 pi stays like this. I end up with x to the 7/3, and that means I got to put a 3 over 7 in the front. I think that's what he said.
Yeah,
Looks
better
good to
at math
me.
than I thought.
Yeah. You too can add 1 to 4/3. That's the hardest part of this whole problem. And then we plug the numbers in. So we get 2 pi 3 over 7 times 1 to the 7/3, and then minus 2 pi 3 over 7 times 0 to the 7/3. That's all 0 over there, so this is just, I guess, 6 pi over 7 if you want to simplify. I hope you got something like that. Any questions about this one? That's a pretty straightforward one. All right, excellent, great. So you will have, that's all I wanted to say about the cylindrical shells. You'll have some ones of these to do on the homework for next week. Any final remarks about the shells? So we have, this is really all we're going to say about using the integral to find volumes of things. We have discussed 2 different methods, the washers and the shells. And, you know, in any given example, you could perhaps try to do either one, although in certain examples, one method is definitely going to be easier than the other one. All right. Excellent. So let's go on to the next section. That was the last part of Chapter 4 that we're going to do. So the next section is Chapter 5. Chapter 4 was mostly about sort of random things you can use the integral to solve. We did the area between curves and then these volumes in 2 different ways. Chapter 5 is about the general topic of inverse functions. And so we're actually not going to be talking about the integral specifically in this section. This is a more general thing about inverse functions. And I hope that you have seen this phrase before. I hope you talked about this a little bit in high school. We're going to try and say some things about inverse functions. Okay, so the basic idea for a function f of x, we can sometimes consider the inverse function. Now, it doesn't always exist, so I'm just going to say we can consider sometimes the inverse function, which is typically written f inverse of x. That little -1 up there means f inverse. In this context, the -1, it looks like an exponent, but this does not mean 1 over x or 1 over f of x. So it means the inverse. This is not the same as 1 over f of x. Even though it looks, this is a sort of overloaded notation. This little -1 sign in this context means f inverse, which is not the same as 1 over x. But anyway, what it means is, the idea here is that f inverse is sort of, I'll put informally, the opposite of f, or you might say it f inverse kind of cancels f, or maybe undoes f, the original function f. What is that? Right? This is the idea behind the inverse function. And you probably have seen many examples of some particular function, and then it has an inverse function. For example, if f of x is x cubed, there is another function whose job is to like undo the cubing. Anybody know what I'm thinking of? A function which is kind of the opposite of cubing something.
Cube root?
Yeah, the cube root. That's the point of the cube root, is to be kind of the opposite of cubing. So if f of x equal x cubed, then the inverse function is the cube root. That's the whole point of the cube root. Like if someone asks you, what does that cube root even mean? The answer is something like, well, the cube root means it gives you some answer whose cube is the original thing that you started with. Like the whole point of the cube root is that it's kind of the backwards or the inverse or the reverse of cubing, all right? And the reason that these are inverses, so what I said up there is that f inverse is supposed to cancel or undo the f. The cancellation, specifically, the way in which it cancels is this, that x cubed, if you do x cubed and then take the cube root, what you end up with is x again. So if you start with x, you do x cubed, and then you do the cube root, you get up with x again. That's not what I meant to say, but you know what I mean. And also, it can cancel the other way around, right? It's also true that if you start with x, do the cube root, and then cube it, you get back to x, right? So this is the kind of cancellation or undoing that I was talking about before. All right. Another way to write this is like this. F of f inverse of x is x, and f inverse of f of x is also x. This is what I mean by the f and the f inverse. They cancel each other out, right? If you do the f inverse first and then do f to it, what happens is you end up with just x again. Now, the cube and the cube root are inverses. That's the whole point of what the cube root is supposed to mean. In other cases, it's not so obvious what the inverses are. So, for example, if f of x, and sometimes it can be just sort of somewhat strange. If f of x equals 1 over x, then f inverse of x, well, let me do a simpler example first of all. What if f of x equals 2x? Then f inverse of x. If you multiply by 2, how do you, what's the function which undoes that operation? What do you say?
X over 2.
Yeah, this is x divided by 2, right? Everybody knows the opposite of adding 2 is dividing by 2. So if f of x is 2 times x, then f inverse of x is x divided by 2. Or if f of x is x plus 5, then the opposite of that, or how to undo that, is x minus 5, right? This is how you undo addition. But it's kind of you have to just sort of think independently about each example. So for instance, here's a somewhat stranger one. What about f of x equals 1 over x? Then what is f inverse of x? If you go 1 over x, how do you undo that operation? This is a little weird.
Multiply by x. Right? You just multiply by x.
So how would I write that? F of x equals?
X.
Yeah. This is actually not quite right though, because this function says divide by x. This function says actually you start with x, you get x again. You could try and think of this in terms of an example. If I start with, say, x equals 2, then 1 over x is 1/2. What is the function you have to do to 1/2 to get back to 2 again? That's what I want, right?
Would it be x squared?
It's a decent idea, but it's not x squared because you will notice if I have 1/2, I want to get back to 2 again. If you square this, you get 1/4, which is not going to get you back to 2. I think this is a little weird, but I think it's 1 over x again, right? If you think about what procedure do I have to do to undo the operation of like doing the reciprocal, the answer is you do the reciprocal again. That will undo the original reciprocal that you did. Slightly strange. So the basic concept I hope is familiar to everybody, but it's a little weird how do you actually figure out what the inverse is? At least when I'm writing it this way, it's not so clear. You have to kind of think carefully about it to decide what the inverse is. You can also, inverses are useful in the real world. So how about a real world function? How about, let's say that f of t represents how tall I am in year t, like of my life. Over time, of course, your height increases over the duration of your lifetime. And you can make a function out of that. Looks something like this, probably. Like after a while, you reach some kind of maximum height where you stay for the rest of your life. Anyway, what would the inverse of that be? If f of t represents how tall I am in year t, then f inverse of, I'm not gonna use t anymore for reasons that you'll see in a moment. I'll call it f inverse of y. This means, anybody want to say what this would mean? It's kind of the function which means the opposite. F of t is how tall I am in year t. This would mean something like, in what? Why did I call it y? I didn't mean to call it y. I meant to call it h. I mean, you can call it whatever you want, but this is to be a little suggestive about what this function means. F inverse of h would mean in what year do I reach height h, right? This is the opposite. So f of t takes a time and tells you the height. The inverse should be the other way around. It takes a height and it tells you the time, right? In what year, that's why I called the variable h for the inverse. In what year do I reach a certain height? It gives you the time associated with the year. This is the opposite kind of function. Describes the same relationship, but the other way around. Instead of giving you the height for each time, it gives you the time for each height. All right? This is how the inverse works sort of in the real world. Or something like, how about f of x is the cost of x pounds of, I don't know, sugar? What would the inverse of that be? So this tells you f of x is, how you say how many pounds, I tell you how much it costs. The inverse would be the other way around. You say the cost, I tell you how many pounds you can get for that. So the inverse would be something like f inverse of, I'll call this p for price. This would be the amount of pounds of sugar with price p. How much sugar can I get for this this much, right? Both are useful, the inverse has an important meaning in the real world. That's what I'm trying to say here. All right. One more way we can think about the meaning of inverse functions is just this. This may be the simplest way at all. How about inverses on a chart of data? If I have some function like this, so if f is given by just telling you x values and their associated y values, and of course, if you're using a chart, you can't write down every single value, but I'll write down some values. Let's say when x is 1, f of x is 6. When x is 2, f of x is 2. When x is 3, f of x is 1. Then I got 5 here, then I got 0 here. All right. If f looks like that, then f inverse is going the other way around. So I'm going to write x and f inverse of x, but it's the opposite way. So when I see in the first case, x is 1, f of x is 6, that means the inverse works the opposite way around. So when x is 6, the inverse of 6 would be 1, right? I'm just reading the same chart, but with values the other way around. So 2 and 2, I get 1 and 3, 5 and 4, 0 and 5, right? If I have a chart of data, the x values have their corresponding values of f of x, and the inverse is the function which just is the complete opposite, right? Each of the, what used to be the f of x values are now the x values, and then the what used to be the x values are now the values of f inverse. All right. These are a few different interpretations of, or ways to think about inverse functions. It seems like a simple idea, but it's a little tricky, all right? And I would like us to notice, we've only got a moment left here, but just notice that we'll have a problem if any values of f of x are repeated. For example, if I try to do the same thing with the chart, but I had a function like this, if x, let's say 1, 2, 3, 4 like that, and the values are 3, 0, 3, 2, if any values of f of x are repeated, what I mean is like this, right? You'll see 3 appears both times in the f of x column. What's the problem with that? If I try to build the inverse, then f inverse looks like, well, I'll just do the same thing. X, f inverse of x, and I read all the columns backwards, so this will say 3 and 1, 0 and 2, 3 and 3, 2 and 4. Can anybody say, what's the problem with that? I just did the same thing. The fact that that 3 is being repeated actually is an issue here. Any thoughts? What do you think? I see somebody nodding. Yeah.
You can't have two like the same inputs for your x.
Yeah, it's because in this case, I have the value here, 3, is being repeated twice, but giving me different answers for this function. The problem here is, now, what exactly is f inverse of 3? According to this chart, it seems to be 1, but it also seems to be 3, right? I have two different answers. It looks like it should be 1 on the chart, but also it should be 3 on the chart. And a function is not allowed to have two different answers, all right? So here, this is a problem since we got two answers. So in this case, f inverse is not a function. This is what I meant when I said at the very beginning, when you start with a function, you can sometimes make an inverse function. You can always make something like an inverse, but in this example, you see that the thing that you get is not a function, and so that's undesirable for a lot of reasons. You know, generally we want to talk about functions, not other things. So in order to make an inverse, I'm just going to say one last thing here. To get an inverse function, f of x, the original function, must have no repeated y values. All right, and the fancy or the technical term that we have for this, I'm going to put this in quotes. This is how we say this. F must be 1-to-1. 1-to-1 means that none of the y values are ever repeated when you look at all the possible y values. So, and you can actually tell on a picture if something is 1-to-1 or not. For example, this function here, this is 1-to-1. Because you will notice, apart from this little thing down here, I didn't mean that, every y value here, if you just look at all the various y values, there's no repetition of different y values. This y value here occurs only right there. It doesn't occur anywhere else on the graph. Versus something which is not 1-to-1 is something like that. This is not 1-to-1. because there are some places, actually over here is no big deal, but there are some places where y values are repeated. Here, there are 3 repetitions of that same y value, and this is not allowed for a one-to-one. So the one on the left is one-to-one, the one on the right is not one-to-one. All right, and I think our time's up, so we're going to continue talking about inverse functions next time. All right, do the homework. Next time is our first quiz. Remember, the quiz covers only what was on the homework assignment. So all this business about volumes with the washers and the shells were not on the homework, so they will not be on the quiz on Friday. So it'll just be about basic antiderivatives, definite integrals, and the u substitution. Any questions about the quiz before we say goodbye? Nope. We're just going to start off with the quiz, first 10 minutes or so, and then go on with the rest of the class. No big deal. All right. Great. I'll see you all on Friday then.
Thanks, Professor. Take care.
Bye-bye.
Thank you.